Hello. In this segment, we're going to be talking about memory performance enhancements. If you recall from CPU pipelining, this works on the assumption that all the stages in the pipeline take exactly the same amount of time, one clock cycle. Unfortunately, access to memory is actually several orders of magnitude slower than the CPU. So, how is one cycle memory access actually achieved at this stage in the pipeline? There are three complementary approaches to improving the performance of memory. These are wide path memory access, memory interleaving, and cache memory. All three are going to be used simultaneously in a system design. The first is wide path memory access. So, memory has high latency, but also high bandwidth. That's what we need. Latency is the amount of time it takes for a round trip. That is, from the time when we assert the chip select and the read-write signals until the data is in the MDR. That takes a long time. But bandwidth is the amount of data that can be returned per unit time. So, pipelining is going to actually increase the bandwidth. So, each instruction still has the same amount of latency. That is, each instruction takes 5 clock cycles to execute regardless. But the pipelining process has actually increased the number of instructions that we can execute in a single time slice by executing 5 simultaneously. So the bandwidth is increased, but the latency is the same. We're going to try and increase the bandwidth for memory. So, memory bandwidth can be increased. To do this, we don't go out to memory and read just 1 byte at a time. Instead, we might read 4 or 8 or even 16 bytes at a time. And to do this, we're going to have a much wider bus between the CPU and memory. The second approach is memory interleaving. In memory interleaving, we're going to distribute the addresses that we're going to read from across a series of blocks of memory so that the memory requests can be executed in parallel. Here's a picture. Notice that we have several memory address registers and several memory data registers. Each of these are individual blocks. This is what's called four-way interleaving. And so each of these 4 banks of memory can be accessed simultaneously. But since memory requests are typically for contiguous addresses, then what we're going to have to do is have a very wide data bus. This is where our previous technique comes in. So this bus needs to be at least 4 bytes wide so that we can satisfy a 1 byte read from each block of memory. The last performance enhancement technique is called cache memory, and this is the only technique that tries to minimize the latency as opposed to maximizing the bandwidth. It turns out that dynamic RAM has a very high latency, but is relatively inexpensive to put in your computer system. Static RAM, on the other hand, is very low latency, but is, conversely, very expensive to purchase. So the idea here is to use a small amount of expensive static RAM as a buffer against the large amount of dynamic RAM that we have in our computer system. So, by analogy, this is like the difference between going to the supermarket when you need to get a new can of soup versus going to your pantry. Your pantry is a cache for what's in the supermarket. It's very low latency. I can walk over to the cupboard, I can pull out a new can of soup, and I can have it within 15 seconds. Whereas a round trip to the grocery store to satisfy that same request might take 30 minutes or 45 minutes. In the same way, we're going to put a block of cache memory that buffers between the CPU and main memory in our computer system. A cache hit is when the data that we request exists in the cache already. That means that we go to our cupboard and we find the can of soup that we want right there. A cache miss is when the data is not in the cache. So we have to drive all the way to the grocery store, we have to buy the can of soup, and then we can put it on the shelf in our cupboard, and then we can retrieve it from the cupboard very quickly. It turns out, though, that hit ratios in current computer systems can be as high as 90%. So only 10% of the time do we have to take the extra trip to memory. In a cache memory, the cache entries consist of a tag, that is, the address of the data that we want to read from memory, the data itself, which is a copy of what's in memory, and what's called a dirty bit that indicates whether or not the data in the cache is newer than the contents of memory. Because it turns out that when we do a write to memory, that's just as slow as trying to read from memory. So we'll write to cache and mark it dirty, and then eventually we will copy that to memory. There are many different kinds of cache replacement algorithms. Eventually, the cupboard becomes full, and we're going to have to eject some of the information out of it. So, what approach are we going to use for ejecting data from our cache? The most common is what's called least recently used, or LRU. Whichever piece of data in the cache we haven't accessed most recently, we'll eject that and then use that spot for a new piece of memory. Other approaches are the first in is the first out. This is a variant on least recently used, but is a queue. There's also least random and so on that are possibilities. What should we do with a memory write? I mentioned this before. We have to keep track of this with a dirty bit. There are two approaches. When we write to memory, we can write through, which is to say that we write to the cache and then immediately put a request in to write to memory, and we wait until the memory write completes before we go on processing. This is very safe because the cache is always in sync with memory. It's very simple, but it's also very slow to wait for that memory access. The other approach is to use write back. When we write back, we write only to cache, and we set the dirty bit to indicate that the memory in the cache is newer than the memory that we have in main and primary storage. And when we go to replace that cache line, we know that we have to copy that contents out. So it's only when we eject that particular line from cache that we do this. And this works out very well because we are frequently incrementing variables in a loop, and this way we only increment those variables, for instance, in the cache, and we don't have to do a write back until we eventually eject that particular variable from the cache. This is complicated, but very fast. Cache coherency, that is, keeping the cache synchronized with main memory, gets particularly tricky when you're dealing with multiple cores in the CPU and multiple levels of cache, because they all need to be synchronized even across the various cores. So, in summary, latency is the round-trip time that's needed to deliver a single request. Bandwidth is the number of requests that can be fulfilled in a particular unit of time. There are three ways of improving memory performance. One is to have wide path memory access, which is to say we increase the bandwidth to memory by fetching multiple bytes at a time. How do we achieve that? We achieve that by using memory interleaving. This is also a bandwidth increase approach. And by doing this, we distribute our reads across multiple blocks. And finally, cache memory tries to decrease latency to memory by having fast copies closer to the CPU. But we have coherency issues where we have to keep these pieces of memory synchronized with the cache.